Hello everyone and welcome to the new lecture of Motion Control Systems class. I changed the systematic a little bit. Earlier in my first video recording I was using a mechanical system here and I was trying to make my derivations on a paper with the camera positioned to see the paper. But now I have a better tool. I purchased myself a tablet so that you can see my notes, my lecture notes directly on the screen, and you can see me at the corner of your screen now. Well, I hope all of you are healthy and all of you are all in well condition. Uh, what I want to do today is to first look where we are, where we stopped last time, and move further for some new topic. That's actually, we will be starting to play with systems that include multiple components. Let's have a look at what we have done so far. Let me go through the pen and let me start writing for you. Okay, so far we have gone through several items. At the beginning of our lecture series in motion control, we had a general overview of mechatronic systems in total, and so we tried to draw specific connections between the subsystems and relations with motion control. So that's what we had in the first week of the lecture series of the class. Then we started the modeling phase, modeling the dynamics of the system, and we made a review of system modeling. Oh, sorry. And we moved further for the derivation of Lagrangian dynamics of a system. So let me take a note of this also for all of you. Lagrangian dynamics. Well, uh, I apologize, by the way, right from the beginning that I'm just very new to this new type of teaching and new media. So I apologize for any kind of mistakes from the very first time, very first seconds. I hope I'll be used to this new systematic soon after a couple of lectures. So after the second week, we moved towards the modeling of electromechanical systems. Well, I might electromechanical systems, where we learned the basics, the main operational principles of how a motor works, which will be the main component for our applications because, as I was always telling you, more than 90, maybe 95% of the applications in the robotics world, in automation world, in general motion control, benefit from the servo motors, DC motors. In general, we can call them electromechanical systems. After we have gone through this main introduction section for the first couple of weeks, we started the new chapter, and I told you there that we will have segment by segment the episodes of the lecture, the weeks between the third and let's say the sixth week were dedicated for acceleration control, robust motion control fundamentals, the disturbance concept. Let me try to write them one by one here. So we introduced introduction to acceleration control. And from the acceleration control, we came to the point that if we have certain tools, our systems will be able to trace the desired accelerations, the demanded accelerations from the system. And there we introduced the disturbance observers. Sorry for those errors. Sometimes my pen is giving some errors. I don't know why. Well, we learned the concept of disturbance rejection, which was one of the main items to be dealt with for robust motion control for high precision systems. And if you remember, while going over the acceleration control chapter, I was putting there a magical box where I was giving the inverse dynamics of all of the disturbances, assuming that they are known. And here, in this week, in the disturbance observers chapter, we have learned that not all of the disturbances could easily be modeled, but sometimes they had to be estimated, and the disturbance observer concept, actually we were abbreviating it as DOB, the disturbance observer concept was there to estimate or get, let me say, measure the disturbance of the system. So in the following week, we moved to the control of force, and we have introduced, once again, these errors, sorry, introduction to force observers, let me say. Well, I think we can change this notation, and the observer we are talking about is the reaction force observer. Reaction force observers. Well, that was called RFOB. Now, if I segment the course into several episodes, I can easily claim that the first part, this part, is basically a review about the fundamental concepts and why we need motion control. This part is an introduction to the basic tools that we will be making use of throughout our derivations for a variety of motion control applications. And once we have done with the derivations or the formulations of these items, then we started the control action. I'm calling this the controller design for single degree of freedom systems. And if you remember, under this title, we have gone through several different controllers. Let me mark them one by one. We had 4 main controller types for the single degree of freedom systems. The first one of the controllers that we have covered so far was the velocity controller, right? So velocity controller. We have started with this because this was the easiest to formulate. We just needed the first order differentiation to obtain the desired acceleration for the acceleration control. And from the velocity controller, we moved to position controller, where we have covered the framework which required second order differentiation. The fundamental reason for this was the position signal itself is the zeroth order signal, and in order to reach the acceleration dimension, you need to have 2 times derivative. So you need twice differentiation, and the formulation of errors for velocity control and position control were different from one another. And then we said that sometimes we can combine velocity control and position control together to reach to something that's what we call as generalized error control. Let me also take a note of this. Generalized error control. In generalized error control, we were specifying our error as a linear combination of velocity and position. And then we were finished with the controller part related to the velocity and position, and we started, actually that's what we have done last week, we moved towards the force controller, and there we have gone through 3 main methods to be covered. The first one is pure spring environment. The second one is spring plus damper environment. And the third one is force control with velocity feedback. So, if you remember that spring damper environment's result was actually a different expression of the force control with velocity feedback, and the difference between those two was that if you have a force controller with velocity feedback, your system first approaches to the target in a velocity controlled manner, so it prevents the impulse over the target. It gently touches the target, and then once the reaction force comes into picture, once reaction force exists, you start to control the reaction force. These were the items that we were discussing in the previous few weeks. Now let me also take them as another episode of the class. So I can call this the first section, the second section, and the third section. Well, first section is once more about the introduction, about the main concepts. The second section is introducing the tools that will be used throughout the course for all of the derivations. And the third section was dedicated to single degree of freedom control systems design. Well, of course, not all of the systems are single degree of freedom. Let me move to my next slide. Sometimes, actually in most of the applications, we're facing with systems that include multiple single degree of freedom components. We call them multi-degree of freedom systems. So, let me call this new chapter. Well, in the new chapter, we are going to be dealing with systems containing multiple single degree of freedom components. Or in other words, sometimes we refer to this as the multi-DOF systems. Well, if we have to talk about this multi-DOF systems concept a little bit, I can tell you that it has several distinguishing features that could be treated with care. First, a multi-DOF system is consisted of several single degree of freedom systems, which means that at the joint level, You can control every subsystem with an independent controller, and that's what we will be calling later on in the robotics class the independent joint control scheme. But unlike the single degree of freedom systems where you have disturbances acting on the system that originates due to the dynamics of only one motion control component, in multi-degree of freedom systems, you have disturbances coming from the uh, other joints other joints in the system. Let me express this a little bit differently. Well, if you have a two-link robot, let's try to write it here. Let me write it as an example. Well, maybe green is better to put here. Example. So if you have a system where you're trying to control just one arm which has gravity on it, which has certain friction force, maybe other forces, stiction, etc., and which might have F external acting on the system. The control action you generate here is the single degree of freedom controller. Well, for multi-degree of freedom or for systems with multiple components, what you usually have is this. You have the first link and possibly a secondary link attached on the first one. Let me try to draw it better for you. So you have the first link and let's say a second link here, which is connected at the joint point. Well, if you're trying to control this system, then you have to take into account the dynamics. So action from system 2 on system 1. Well, it's easy to argue that the action from the second system on the first system is nothing but a different type of disturbance, and the disturbance observer in the first system will be able to compensate that. That's true, but in order to create a complete picture for the general control of multi-degree of freedom systems, we have to carry out certain different analysis. So, if I wrap up my words, if we are interested in controlling multi-degree of freedom systems, our control in the context of motion control systems class will be again in the joint level. So we will be covering the independent joint control structure here, but we will take into account the overall dynamics from the multi-degrees of freedom systems, multi-DOF systems. So this was kind of a summary example about the change between single degree of freedom and multiple degree of freedom systems. Now let me move to my next slide. And let me change color back to yellow. Well, today's topic will be controller design for systems with functional relationships. So I'd like to deal with, so let me write here, controller design for systems. I can actually write here with multiple degrees of freedoms. Oops, that's not DOF. DOF is disturbance observer. DOF is degrees of freedom. So controller design for systems with functional relationships. And we will go through case study 1, which is grasping force control. Now, uh, when we say functionally related systems, or when we're talking about functional relationships in a system, we're basically referring to a system with multiple components where there is a task to be completed in a collaborative manner by those subsystems. So that these systems are called functionally related systems. So there are some functions, there are some relationships, or there are some task-wise definitions that these systems have to take care of. And we will start by a case study, which is based on grasping force control. Now, in our example, let me change the color for the derivation. In our example, we will go through a well-defined system. Let us assume that we have, let us assume that we have a system where we have an object to be manipulated by two actuators. Don't forget that the simplest multi-degree of freedom systems start with 2 DOF because, you know, the smallest number bigger than 1 is 2. Well, here we have an object. Let me try to draw you the object. Well, I think using a different color for the object would be a better idea. So this is our first actuator here. Let me draw a second actuator somewhere here. Well, I think no. I think somewhere here it might be better. So we have two linear actuators, and in between those actuators we have an object. Let me show you the object. This is our object. So we're assuming that an object is positioned between two actuators and is to be manipulated by those two actuators. So we're calling this as grasping control. Why is it so important? So we have so many tasks where robots are dealing with grasping. So pick and place operations are one of the most common examples of the tasks that the robots have to carry out in the industry, in personalized applications and so on and so forth. Furthermore, if we are talking about collaborative robotics, now the robots nowadays are being used as devices to assist the manpower. If we are talking about collaborative robotics, we will also have grasping control duties in most of the applications, or in many applications, I can say. That is simply something like that. You have an object to grasp. So one of the actuators is coming from one side and the other actuator is coming from the other side. So in order to hold the object, you have to preserve certain force on the object. And once you preserve the force, once you trace your force control objective, your second objective comes. You want to move this to somewhere. That's called grasp and move. And now it's time to make the formulation for this. Let me also make my axis definition here with a different color, maybe green. Yeah. So assuming that this is the point where we make our from where we make our measures, and this system can easily be called the master system. For simplicity, you can call this system as the slave system. These are just hypothetical names. You can call these systems as, system 1, system 2, or whatever. Master slave is just for ease of notation. Well, if we call the coordinate if we call the coordinates, we have to define several ones. So this is 1. I will tell you that there is, no, not that one. I'm sorry. I'll tell you that there is one here and another one here. So this part will be, and this part will be other 2 points to be denoted. And here we have the last point. I'm sorry, here is actually our last point. So I will call this xm. So assuming that this is my reference point, so this is the distance from the reference point to the contact point of the master system. And I can call the next point xme. This is the environment position. So that's actually, hypothetically, after you push your actuator and squeeze your system. Okay? These are, by the way, exaggerated. If you don't have a substance or a material like a sponge, or in other words, if you have something with high stiffness, these exaggerated differences will not be easily observable. So you'll have micron level deflections in the system. But in order to make the derivation, I have to exaggerate them. I'll call this later on. Now, let me further define 2 more axes here. That one and that one. So similar to this one, I'll call this XSE, the environment position of the slave system. So I'll simply call this XS. This is the slave system's end effector position. And this one I'll name as X center of gravity. So we're assuming that we have an object with uniform material density. Let me call it material distribution in general. And second, we know the stiffness and damping of the object. Oops. So this is our object to be grasped. I think so far so good. So let's move to our next slide and start defining some dimensions. So if you go back, if you see here in that slide set, master system is holding on one side, the slave system is holding on the other side. So their collaborative action will create a force on the system to hold the system so that it doesn't fall back. And while tracing your force reference, or while preserving your force reference, you're trying to move this object. So this means that we will basically try to modify center of gravity while preserving the grasping force in that system. So in order to do this, we have to define the grasping force. Let us define the grasping force in the system. Well, for the grasping force, we may have a look at the figure here, and we can assume an environment with certain stiffness and damping. If we recall from the previous lecture set, the damping times the deflection in the environment plus the stiffness times the deflection plus the damping times the derivative of the deflection. gives us the force generated in the system, and those stiffness and damping are environment related parameters. They're environments, and they're the portions of the environmental impedance in the system, let me say. So with this notion in mind, we can define the force on the master side. So force on the master side can be defined as follows. Fm is actually equal to master system's stiffness constant, so that's the spring constant actually, times x master minus x master environment plus master systems, I'm sorry, that's not master system, that's the environment, right? Don't forget that we have one environment here, we have one object, and it has specific Ke and De, all right? So we have the force on the master side is equal to Ke times the master side deflection plus De times the derivative of the master side deflection. That could be called Xm minus Xm environment, of course, dot. So you may ask, I'm sorry, I cannot put a dot here. Okay, you may ask me, last week we were ignoring this component. Xme dot was assumed to be 0. That was because our environment was assumed to be stationary. But now environment will also be moving. Recall that our objective is to grasp this object and move it in the right-left direction, right? So this can be a good model for the force generated on the master side. Let me write in a similar manner the force generated on the slave side. Force on the slave side. It's nothing different. It's actually very similar. F slave is equal to, now we have a change of sign, minus Ke times x slave minus x slave environment plus De, I'm sorry, this is again minus De x slave dot minus x slave environment dot. Well, the minus sign is obvious for most of you, but I have to express this once more. It's basically due to change of dimension. If you look at the first expression, it's Ke times Xm minus Xme plus De times Xm dot minus Xme dot. So it's nothing but stiffness times the deflection plus damping times the deflection's derivative. That's the force on the master side. In a similar manner, stiffness times the deflection and the damping times the deflection's derivative should be the force on the slave side. But look at this. Slave side force will be towards right, right? That's why we have a minus sign here. It's because of the change of direction. Okay? So, having defined this, can we formulate a term for grasp force? Can we formulate the grasping force? Let us formulate the grasping force. The grasping force can simply be given as F grasp is equal to summation of the master side force plus slave side force. So this is a fundamental term that we shouldn't forget. In other words, we can define here in a long way that the grasp force is nothing but Ke times Xm minus Xme plus De times Xm dot minus Xme dot minus Ke times xs minus xse minus dE times again xs dot plus xs environment dot. So remember, these were all defined in the previous slide This is the grasping force we have in hand. Let me also mark this equation for you, because we will make use of those definitions for our controller derivation. Let's move to next slide. So, can we simplify that? We will actually. So, let's write here. Make a trick. We will change the coordinates. Change coordinates. How can we do this? We can actually define the following. Let's write define Qm to be xm minus xme and Qs to be xs minus xse. Okay, so these two new definitions will simplify our life when we're looking back at this grasping force equation. It's nothing but calling the deflection in a new dimension. Here Qm is simply the deflection here, and Qs is the deflection on the slave side, right? Qm, Qs, and of course their derivatives. Qm dot is the rate of change of deflection. Qs dot is the rate of change of deflection on the right hand side. So, with these definitions, we can rewrite the grasping force as follows. F grasp, the grasping force is nothing but when you substitute these two back to here, you're gonna get Ke times Qe plus dE times Qe dot. I'm sorry, Ke times Qm. Let's write here. Ke times Qm minus Qs, I will say, because remember Qs was this. So if you go back to that equation, Ke times Qm minus Ke times Qs is here, right? So Ke times Qm minus Qs plus dE times the environment damping times Qm dot minus Qs dot. This is the new definition for our grasping force. Well, I think so far so good. What we have done basically was to define the grasping force in a system like that one. Here, we should keep in mind that the object's center of gravity may change its position. We haven't yet defined this, by the way. Well, once we have the grasping force definition, can we write the grasping force error? Obviously we can. How can we formulate the grasping force error? That's our question. It's not so difficult. We will make an assumption here. Assumption. We will assume that our grasping force reference, so F grasp ref, exists and is different, continuous and differentiable. What this means is that f grasp ref already exists and it's continuous. We can take a derivative of that and we can reach to f grasp ref dot, right? So keeping this in mind, let us formulate the grasping error. Grasping error. I'm sure that most of you would immediately jump and tell that it's nothing but reference minus response, right? Here, in order to show the derivation in the other way around, I'll just make a change of sign and define our grasping error as E grasp is equal to F grasp minus F grasp reference. So what we were doing until now was simply reference minus response, but now I changed to response minus reference. Does it make any difference? It only makes difference in the transients actually. You know, if you define it to be reference minus response, your error will start from some value and go to 0. Let's assume that you have a positive error, it will start from positive value and go to 0. And if you change the sign, you'll have the same error from negative side, but if you formulated your controller again in an exponentially decaying manner, your error will converge to 0 value in the negative side of the transient, but eventually you'll have 0 grasping error with the method we were applying so far. Actually, we can write the content of f grasp and we can define it in a better way. So E grasp, the grasping control error is Ke times Qm minus Qs plus dE times Qm dot minus Qs dot. So this part until now was the grasping force minus the grasping force reference, F grasp ref. I will highlight this for you because this one will be important when we're making our derivation in the coupled system. So far so good. But this is not enough information. Until now, we have only formulated the grasping force in the system and how we can define the grasping control error so that we can move the error to 0 value, which means that we will be able to trace the grasping force reference. So if you have sinusoidal force reference, if you're trying to press and release your system, you'll have F grasp ref as a sinusoidal function. But this is not enough, because we have two systems, the master system and the slave system, and two systems can follow two objectives. Take my note, it's important. The number of different degrees of freedom in the system means that number of different tasks to be completed, different single degree of freedom tasks to be completed. So we can define, we need a new definition here. Let me erase this. And let me write here the error in the center of gravity. So we will make a new definition that is center of gravity. Let me try to express this in a better way. Define position tracking objective. What's the position tracking objective? It is simply following the reference, the center of gravity. I call it a COG reference of, actually not of, that's for the object under consideration. In order to accomplish this task, we have to first define the center of gravity. So define COG. I'll write you simply here. QCOG, center of gravity position, is nothing but QM plus QS over 2. Right? So if you go back to the figure, if you deflect this side by 3 centimeters and deflect this side only by 1 centimeter, it's easy to claim for a homogeneous object that 3 from here, 1 from here, 3 minus 1, it's 2 centimeters, and it's the division by 2 yields to 1. So your center basically moves only 1 centimeter to this side. Okay? So, of course, when we define the center of gravity, our next error, which is the position tracking error, comes naturally. Position tracking error. Let's go back to the same to the previous slide and try to stick up with the same notation. So you have E grasp here. Let's write here. E center of gravity is nothing but Q center of gravity minus Q center of gravity reference. It's the same philosophical discussion here, or the argument here, that it's response minus reference, but nothing changed. We will again try to push the error, response minus reference error, to 0 value with our controller. So if we expand the content of QCOG here, our center of gravity error can simply be written as QM plus I'm sorry, is it plus? Yes. QS over 2 minus QCOG reference. Let's highlight this, just like the part we had in the force. Okay, so far so good. I think it's time to give a break for this class, and in the next class I will start from this point where we have the derivation of the grasping force and the center of gravity errors, and we will try to come up with a controller that controls this and this together. Thank you for watching.